So, question 3. Ooh, now this one is fun. So, first, you want to classify the following pair of compounds, okay? Compounds as same enantiomers or diastereomes, okay? So just to make sure, so enantiomers, I want to make sure I'm explaining this right because it can get quite complicated. So same, let's just start there actually. Same means that the compounds are the same thing. So it means that it's not like a mirror image, it's literally the same compound, as in they have the same R and S in terms of like rotation, and everything else is just, you know, from a different angle. That's why it's very important to do the next steps we're about to do to figure out which one it is. Enantiomers, on the other hand, they're like the literal mirror reflection. So it's like if this one was rotating clockwise in terms of this chirality, that one will be rotating counterclockwise, and it follows suit, as in every single part of it is an opposite reflection of each other. Okay? And diastereomers, hard words to pronounce, those ones are not the exact mirror reflection. It's like one or multiple parts are interchanged. So if this one was like a clockwise rotation, this would be counterclockwise. But overall, there's still that missing, like that piece that's similar, so it doesn't form that mirror reflection. In fact, actually, it would probably be easier to draw it. So same, if this was like, let's say we had a simple compound like this, where it was like R, R, this one would be R, R, okay? Or even like S, S. Because realistically speaking, it's just kind of like looking at a different side. But I would go, if you wanted it to be the same, I prefer if it was just like literally the same thing. Enantiomers, okay, mirror reflection. So actually, same has to be literally the same. Do not, because in this case, that's what an enantiomer is. It'll be like SR. This is a mirror reflection. So, back to what I said earlier, same has to be exactly the same. You'll notice that depending on how you draw it, specifically if you follow the right way, it should end up showing up as the same thing if they are the same. This is what enantiomers look like, and diastereomes look like this. Let's say this was RS, this would be like SS. See, two of the same, but one part is flipped. And then constitutional isomers is when they have the same name but built completely different. Like let's say one was like a ring and the other one was like these two. Technically, if I drew no benzene ring, just an actual 6-ring hydrocarbon, and then this 1, 2, 3, 4, 5, 6, they're really the same thing, because if you actually count 8, 4, 5, 6, oh no, they need a double bond in here somewhere. But point being is like this would be like C6H12, and this one 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yep, this is also C6H12. These two are constitutional isomers. They have the same, they're constituted of the same thing, but they're literally different. And last but not least, not isomeric, just different compounds. So but we're focusing on those 5, okay? And now we're going to see 1 and 2. So now with these questions, we have to actually kind of do the second part before the first, because only by finding out its rotation, its chirality, can you say whether it's actually one of those 5? Okay, so with this, the way you draw this, you have to be very, very careful about this, because it did take me a bit of time. But when you look at this picture, for example, okay, so you have, let's actually draw the whole thing here, because that's a little bit easier to explain. CLH, this is CH3, that's why you don't mention it. CLH, okay, so this is what we have for the first one. So the I'm gonna use a highlighter for this. The bend here shows the parts that are kind of sticking into the page, if that makes sense. Okay, and the top bend shows the parts sticking out of the page. So we have parts sticking into the page, sticking out of the page, and you want to draw specifically to where you're accounting for things sticking into the page and out of the page. Me personally, I drew it, if I was looking at it, if I had an eye view, let me just change this over. I drew this part looking at it like that, okay? So if I'm looking from top to bottom, this is what I see. I see, okay, like that. I see the chlorine at the bottom, you know, sticking into the page. I see a carbon group, the CH3, sticking out to the left. And I see hydrogen, as it's shown there. Because remember, the dashed lines, that just means that it's going away from you. So technically, when you're looking down at it, the hydrogen's on the right. It is very weird, something you have to get used to in terms of this question specifically. Now that leaves that this rest of the thing, the R group, is at the top. That is what I see here. Now, with that though, okay, you have to also keep, in a sense, that same viewpoint, because now I'm looking at this one from here, okay? So you get this picture, and in this area, I get, okay, that the carbon group CH3 is at the top, okay? The R group, like the rest of the chain that expands to the bottom, chlorines to the left, okay, and hydrogens to the right. So that's what I'm seeing. But these two parts aren't enough yet for you to determine which way it's going to rotate. So you notice that the hydrogens for both of them are on the, well, in this case, the right. You want it to be at specifically the top or the bottom, but you want to make sure you do the same change for each one. If you're going to move the hydrogen to the bottom, because in a sense, you don't want the hydrogen to be on the pieces sticking out. And so you have to, in a sense, flip its position with something else. But when you do that, whatever direction you get, you have to inverse it, so that way you get the actual chirality, okay? So let's go step by step. I'm going to flip the hydrogen with the chlorine in this case, and the hydrogen with the R in that case, okay? So I get H is now here, chlorine is here, R, CH3, okay, and I get here Cl, R, H, CH3. Now remember, okay, this is the opposite. But now that hydrogen is, in a sense, out of the way, pointing in to the page, it's like we don't have to count anymore. We do our rotations based on the strongest group, and we move from there. Chlorine is the strongest group, and then followed by the bigger length, so the R, because that's where the rest of the things attach, and then the CH3 comes last. So in this case, if we were to trace, I guess, a circle, because we ignore the last one, we ignore hydrogen. We always ignore the fourth one. In this case, hydrogen is the weakest one, so we ignore that one. That's why I flipped it over. So it goes chlorine, R CH3. So we're getting this rotation here, and that is a counterclockwise rotation, so that's an S. Okay, but remember, this is in the opposite section. And now here we have chlorine R CH3 also going in the counterclockwise position, so that's also an S. So remember, because this is the opposite, our final result is that these two are going to be R's. That is what it is. So that means for this segment, that's an R. For this segment, it's an R. So they're both turning right. So that's the first part. See, this is quite a question. All right, so now the second one. Okay, because now we're on to the second part of this. We have that. And the reason why these questions can be difficult is because you really can't tell what you're dealing with until you write it out. From just a viewpoint, unfortunately, this information is hard to mean much, which is why you have to make sure that you take your steps one at a time. So now let's do the same thing here, okay? Bird's eye view, we're looking down, okay? So what we have is, imagine if I was, this is the nose here. That's a good thing to add because you want to make sure that you see, I want to make sure that you see what I'm seeing, okay? And then this person's head here, okay, his nose is actually going to be, just to make sure this our boy is like that, okay? So it's kind of like someone walked around pretty much and looked at it. Very weird concept, but that's how I understand it. It's just important that we just go through steps of how we're supposed to look at it. You want to make sure everything's, I guess, as similarly done as possible. That way you can actually notice the changes within each one. So here, when you look at it this way, the R is also at the top. We have the CH3 group here, the H here, and the Cl at the bottom. And then for the second part, we have Cl at the top, H, CH3, and the bottom is an R, okay? So same thing here. We want to make sure that the H, preferably at the bottom, just keep things constant. So we flip it over there, and we flip it over there, okay? And now what we get is, as a new thing, so this is now the opposite section again. You got the R, CH3, Cl, H. And now here we have Cl, CH3, R, H. And now let's see what we get when we track the rotation. So start with chlorine, move over to the R, then CH3. So this one is an R, okay? So remember, it's going to be the opposite of that. And here, start with the chlorine, move to the R. So this one is actually going counterclockwise, as an S. So with that, you just flip it over. So now we get S, R as the second one. Whew. So luckily for us, we've actually gone through the hard part. So now we can kind of just draw that next to each other. So we have R, R, and S, R. Now this is not a mirror image. So this, and we know it's the same compound. Well, not same compound, but same constitutional structure, as it has the same things. And we also know that all that's different is literally one piece of it. So it's not a mirror image. So this will actually be a diastereomer, if I said that right. So just in case they weren't sure what I said when I pronounced it, that's what this is here, okay? So now we have that part, and now they're asking for the naming of it, okay? So the way I do this is I kind of just went through process of elimination. So we needed an RR and an SR. Okay. So the only one that has the RR is the second choice. Now you notice that the pairing thing is RS on this one. Now these are very important for these type of questions because there's only 2 chiral points, as I said, and literally like they're the same thing. You don't know which one is going to be the primary carbon and the first carbon and the second carbon because of the fact that you could have started anywhere. I could have made this so like what here, because it says RS, we can say that they made this 1 and this 2, hence how they got the RS. But for me, when I was doing it, as you notice, I start from the top. I made this 1 and I made this 2, hence how I got the SR. So with that, just be careful because you may still have the right answer. It's just important to account for the fact that they may have started from the other side. Just go over it, see where you'd like to attach your first carbon, and then go from there. So this question exactly would be, answer is B in this case. I would love to write out the whole thing, so I'm going to pause it here for you to write down just in case you need this in this example. So compound 1 is 2R, 3R, 2,3 dichlorobutane, okay, which makes sense because there's a 4 CH3s, 4 carbons, and then 2 chlorines. That's it. And compound 2 is 2R, 3S, 2,3 dichlorobutane, also that. So diastereomer, that's what they are. Now let's see if we did it correctly. Oh, no answer. Okay, so we got our work cut out for us. So we can only hope that I did this right. So I'm going to leave that here just for you to quickly take down any notes that you want to. A lot of steps. If you definitely need more explanation on how to do the specifically the chirality, I definitely click on the link in the description below because we have wonderful tutors here and we can definitely further explain how we even get to the point of assigning whether it's R or S. Okay. All right. Now let's move on to question 4.